Okay, welcome everyone. So this is the last Motwani Distinguished Theory Colloquium of the school year. This is a roughly quarterly series of theory colloquia that we have here, aimed at a relatively broad audience. The series is named in honor of our late colleague Rajiv Motwani, who was on the faculty here from 1998 to 2009 and contributed many fundamental results to theoretical computer science, including to the PCP theorem, locality-sensitive hashing, and many famous results in randomized algorithms. So I'm honored to introduce our speaker for today, John Kleinberg. So John is the Tisch University Professor of Computer Science at Cornell, where he's been on the faculty since 1997. So the list of John's sort of greatest hits so far in research is a long list indeed. So early in his career, he developed the idea of hubs and authorities in web search, which was an important precursor to Google's PageRank algorithm. He also pioneered the algorithmic study of small world networks. And for the last 10 plus years, he's focused on really leading the way on both the theoretical and empirical study of social networks, guiding a once nascent research area into the sort of vibrant state that it's in today. So his many prestigious awards include a MacArthur Fellowship in 2005, the Nevelina Prize in 2006, and the ACM Infosys Foundation Award in 2008. He's a member of the National Academy of Sciences, National Academy of Engineering, American Association of Arts and Sciences. And so finally, on a personal note, I've known John since 1998 when he successfully recruited me to join Cornell's PhD program, despite the fact I was a lifelong Californian. And while he wasn't my PhD advisor, his influence on my career and aesthetic, I think, are unmistakable, and I continue to regard him as a peerless role model, as do many other younger scientists. So his talks are always memorable. I'm sure today will be no different. So please welcome John.
All right. Well, thanks very much. Thanks very much, everyone, for coming out to this talk. Thanks, Tim, for the very kind introduction, and everyone at Cornell is very proud to have Tim as an alum, certainly. You know, it's an honor actually to take part in this colloquium series named for Rajiv. I got to know Rajiv during the 1996-97 year when I was a postdoc at IBM Almaden with Prabhakar Raghavan. And sort of, you know, a few things stand out to me really from that year I spent interacting with Rajiv. One was the incredible and sort of instantaneous and unquestioning hospitality and warmth he showed as soon as I showed up in California. I actually was sort of looking back over the mails I exchanged with him as I was preparing this talk, you know, and sort of on my arrival, I mailed him and said, hey, I'm in town, it'd be great to talk, and he immediately said, okay, you know, let's set up a time when we can meet, and I came up to Stanford roughly once a week, you know, and we wrote a paper together, worked on a number of really interesting things, and it really had a big impact on how I thought about things. You know, not just on that postdoc year, but going forward. And I think the big impact really is the part of the second aspect, you know, that I think of from that collaboration with Rajiv, which was that you know, Rajiv and Prabhakar, my postdoc advisor, both I think had this worldview, you know, that has ultimately proved decisive, that CS theory is really this powerful lens for looking at emerging important issues in computing, giving us a very clean way to reason about them, and thereby actually allowing us to solve problems better than we could otherwise and by other means. And so, you know, I think it's great that you guys have started this colloquium series, which, you know, I think really, you know, looking at the list of past speakers, really sort of celebrates the power of theory in a lot of domains and really reflects this worldview that Rajiv embodied. So I want to talk about some particular issues that have been motivating me and a number of colleagues, some of whom are also your colleagues. I'll start actually with a preamble, some work I've been doing over the past couple years with Ashton Anderson, Dan Huttenlocher, and Yuri Leskovic, looking at how people make plans online, how people make plans and attempt to stick to them. That'll be the preamble. And with that as motivation, I wanted to get into what we've been finding to be some very interesting theoretical questions I've been doing jointly with Manish Raghavan, an undergrad graduating from Berkeley, and my former PhD student, Sigal Oren, who's now an assistant professor at Ben Gurion in Israel. So what are these issues that motivate us. I'll start with the stuff that Ashton, Dan, and Yuri and I were thinking about. So there's sort of this growth in sites on the internet, on platforms, where people really make very long-range plans, right? They have what amount to these very long, visible careers on the site. Some examples, Wikipedia, something that I've looked at over a number of years with a number of colleagues, where people can log up to, say, 10,000 edits, at which point they often apply to become a sysadmin on the site, right? An admin who has the ability to resolve disputes, lock down articles, and so forth. And so there's essentially a whole career arc, including what looks to us in academia almost like a sort of tenure and promotion case that happens as you become an admin. These are very explicit goals that people set for themselves and attempt to reach. Stack Overflow, similarly, where people develop enormous reputations, and it eventually almost becomes part of their portfolio as a member of the technical professions. Coursera, of course, where people do online courses, attempt to complete them, stick to plans that they set for themselves. So all these things, reputation, status, promotion, your own individual achievement. And so the question was, as we think about designing sites that get people to formulate plans and stick to them and achieve the goals that they set for themselves, how do we reason about the utilities that these people have and how they go about them? Now, there are a lot of ways of thinking about this. One that Dan, Yuri, Ashton, and I looked at was this notion of badges, right, where we set milestones, and then people attempt to reach these milestones. And what we found actually, in the sort of first pass where we just look at data on people as they approached these sorts of milestones, we saw some interesting things. So let's take Stack Overflow, for example, right? So a page on Stack Overflow looks like this, just so we can get oriented with, what's going on here, right? So people ask questions, people answer questions, and then there are these other components on the site, right? So people, if they like this answer, they can upvote it, and if they like the question, then they can upvote it. Now, there are badges given out for achievement in all of these dimensions, and two that we were looking at the time we were thinking about this were a badge if you voted 300 times cumulatively, right? Because they're trying to encourage voting, because voting is adding really crucial metadata to the entire site. And also, a more extended badge if you vote 600 times on a question. Because questions often get fewer upvotes, and so sort of rewarding that specially is important. So we were sort of playing around with how this process behaves over time. And we thought to look at all the users on the system, and we said, let's imagine their career trajectories on the site, and let's align a time series of their activity pinned to the day on which they achieve a given badge, right? So lots of user timelines, what they're doing, sort of slide them all so that day 0 is the day that they win some badge. What does their activity look like? Right? And this thing jumps out at you that, for the badge where you want to vote 300 times, it's very easy to see what this badge is rewarding, because this is a time series of how many questions they asked, how many answers per day, how many times they voted on questions, how many times they voted on answers, up to day 0 when they receive the badge, right? And it jumps out at you that there's this ramping up as they accelerate toward this milestone that they've been aiming toward. And then, of course, there's this ramp down right afterwards. And it's even more extreme here, where you can tell that this badge is rewarding both activities, and this one is only rewarding question voting, and it goes to this gigantic cliff right at day 0, right? And so,
is there some way to kind of tease apart sort of, them actually ramping up versus you could imagine if people just had maybe like a very heavy-tailed distribution?
Random lifetimes, yeah. So there are other views of this where, for example, we include people who dropped out at all different points, and we look at their distribution activity, right? And that whole distribution is torqued as time goes on. In effect, what was sort of, these are sort of snapshots of a model that we were thinking about where we're looking at your distribution activities based on your proximity to different milestones on the site. And in some sense, even before we located the milestones, you could tell these distributions behaved kind of smoothly through space. You were sort of flowing through space. And then they would begin to sort of steer in certain parts of the space, almost as though there was some object there that they were steering around, and that was sort of where the location of the badges were. So there are definitely multiple ways to look at this. This is one projection just on the people who win the badge, which of course selects for only those people who cross the threshold. But even if you just estimate it at each point, you're basically getting this effect. So it's clear people are sort of reaching toward these goals. And with that in mind, we asked ourselves a few questions, which again are sort of going to motivate, in an abstract sense, some of the theoretical questions that I wanted to look at. Right? So one is the badge placement problem, which I think is actually a very rich kind of incentive design question that we don't understand very well. The badge placement problem essentially asks, the site designer may have a desired mix of actions, a certain amount of question asking, answering, voting, and so forth. Where should you put badges if you want to if you want to create this distribution, this sort of sought after distribution, right? In some sense, the number 300 and the number 600 as milestones, when you talk to people who set those badges, were designed, with some rough estimate of what the users look like, but, it's sort of unclear whether were those the right choices. If not, how far were they from the right choices, right? So sort of with some kind of a model, we could imagine asking these kind of design questions, right? How do I design badge locations or any other kind of incentive that might steer behavior? There's also these questions, how do badges derive their value, right? There could be actually a number of reasons, right? There's a social reason. I see people with badges, I'm impressed by that, I would like to be like them. I imagine that if I have a badge, people will be impressed by me. That's a social argument. There's simply the saliency argument. If I set a milestone for myself, then it's something I can work toward. I achieve a sense of closure when I've actually achieved that milestone. And actually, there are more concrete reasons. There are transactional reasons, right? So the site designer could say a certain badge unlocks your ability to do something on the site, and now you have a very concrete instrumental reason why you might do it. Okay, so these were the kinds of questions that we were thinking about. People setting long-range plans for themselves in the presence of rewards and incentives. The question of design, how do we set up these incentives to get people to achieve what they're looking for? And just this whole question of what are the utilities that people have for themselves? So we thought about this in Stack Overflow. We thought about this actually in Coursera, where we looked at how we created some badges in the online forums to reward activity there. And we were ultimately led to the question of, what are the kinds of models that we should be thinking about for how people are developing these plans? Okay, and so this is how I ended up with some theoretical questions, initially looking at them with Segal or Ren, and then partway through this, Manish also joined us on this. So here was the issue. I was thinking about this problem of how are people thinking about these long-range goals they set for themselves. And of course, making plans for the future is something that has been studied extensively in the offline world, right? It didn't take the internet to create situations where people set goals for themselves, right? And so many examples, so even working toward a high school diploma is something where you're budgeting your time, you're deciding, can I afford to do this extracurricular activity? Can I afford to have this job after school? You're doing many things that try to get you toward this particular thing, right? There's a checklist of things. And actually, the Tacoma public school system, for example, decided to really drive this point home by replacing their flowchart with a treasure map filled with buried treasure and quicksand that you might fall into as you attempt to reach your high school diploma, right? This sort of path that you have to follow. Actually, sort of an echo of some of the graph structures that we were playing with that you might try traversing as you try reaching goals. Okay. So when you look at the literature on making multi-step plans, there are some recurring steps, right? Plans, can involve a sequence of things, some choices that can send you this way or that way. And a natural model is to say agents are optimizing some objective function, right? The reward at the end, perhaps. And they're going to choose an optimal sequence of actions given the costs and benefits, right? You incur costs by doing certain things, right? I incur costs by not taking a job after school to improve my grades. And I get a benefit, like a high school diploma. So what could go wrong, right? We know the costs and benefits, we make some plans. Well, one could just be, the cost and benefits might be unknown to you, you have a distribution over them. They could also change, right? That could go wrong with your plan. So it could be that you're moving along just fine, and then both your parents lose their job, and now suddenly the whole conditions under which you're operating change. But there's something else that happens, which is time inconsistency, which is the particular phenomenon which I wanted to zero in on, because it's really a fascinating issue that I think could sort of benefit from thinking about it in the sort of framework I'm talking about here. So time inconsistency means that you create a plan for yourself, and then without anything in the cost structure or benefit structure particularly changing, you simply don't follow through with what you planned on doing, right? Where do we recognize this? Well, health club memberships are certainly the textbook example of this, because on the first of the month, you say, this is the month I'm going to really get in shape. It's going to be great. This is in Britain, so I'm going to spend my £19.95. I'm going to join the health club, and I'm going to get up at 6 a.m. every morning, and it's going to be great. I'm going to get in shape. And then the second of the month comes, and 6 a.m. is really early, and you really don't feel like doing this, and so you don't, and then the next day, and so forth. And so nothing particularly changed. It was not that you sprained your ankle and couldn't go to the gym. That's not what happened. It's just you didn't feel like following through on it, right? Your perception of the costs and benefits were different later in the month than they were on the first of the month when you optimistically made this plan. That's time inconsistency, right? Your reasoning is inconsistent across time. Okay, so this turns out to be a very rich literature in behavioral economics, and time inconsistency is sort of one of the sort of top-level biases that people think about. And because we were in the process of thinking about how do I design for people making long-range plans, it sort of seemed important to try merging these two strands together, right? So the literature on time inconsistency had a lot of fascinating stories, a lot of fascinating case studies, such as the health club membership, such as planning toward graduation from school and so forth. And trying to sort of integrate all these stories using the models that people constructed was proving to be challenging. And so our question was really, could we come up with a model that unified all this, where we could reason about it in a kind of consistent way, and even maybe just try to derive some of these conclusions mechanically or algorithmically? Okay, so in order to set up what these models are, we start from some very basic models arising in the behavioral econ community. And so one of these models actually dates back to the 50s and 60s, but was described very colorfully in a short paper by the Nobel laureate George Akerlof. And I can sort of describe his paper under the heading, "Why did George Akerlof not make it to the post office?" So here was the story that he told in his paper, and this is really just my retelling of it. He was on sabbatical in India, and the end of the sabbatical was coming. And he had this gigantic cardboard box of all his possessions he had to ship back. Okay, so that meant he had to, at some point before the sabbatical ended, the sabbatical ending in N days, he has to make it to the post office and send it back. And of course, actually there was people back in the US who were actually gonna use this stuff. So every day he didn't do it, there was actually like a minor sort of loss of use cost for the people back there, which he also internalized for himself. And so the goal was to ship it as fast as possible because, then they'd be able to use it. But the problem was, it's gonna take half a day to get there, you have to stand in line, fill out lots of forms, it's gonna be an incredible pain. And there's just lots of, things getting ready. Okay, so that was his thing, right? There's this one-time effort cost, which is non-trivial, it's a big number, C. You're gonna lose a half a day doing this. And then there's a sort of minor loss of use cost, X, each day that you don't ship it. But you do have to ship it back. So basically he was facing the following challenging optimization problem, which is if you ship it on day T, the cost is C, the one-time cost, plus T times X, all the days you waited times X. And your goal is to minimize this over all T between 1 and N. Okay. And if you think about that, the way to minimize it would be to set T equal to 1, which is do it right away. I mean, there is absolutely no value in waiting. But he did something that, you might, I certainly would recognize in my own behavior. He didn't do it on the first day, because who wants to spend half a day standing in line at the post office, right? So he was the actual agent of the story, and he procrastinated, right? As he tells it, each day he planned he would do it tomorrow, right? No, not at some particularly carefully chosen, right, tomorrow. And so, of course, the effect was, if you always plan to do it tomorrow, you wait until day N when you have to, you're either going to ship it or you're going to abandon it. So he ships it, paying the cost of C after all, and at a much higher cumulative cost. There are various twists to the story that aren't relevant here, including the fact that roughly day N/2, a colleague took pity on him and was going to the post office anyway and took the box with him, and so it didn't quite turn out this way. Okay, so this is what happened. It's something that's very recognizable. He did something that maybe not all of us would have done, which is he decided to sit down and model his own behavior. He said, if I did this and if everyone I know does this, there must be something robust about what I was doing. Let's figure out what that was. Okay? And so in doing that, he drew on some writing on inconsistent decision making from the 50s and 60s. And he said, suppose that agents suffer from this thing we'll call present bias, in which costs that you incur today are simply more salient than all costs you incur in the future. I'll mention discounting in a couple sentences. This is different from geometric discounting, if you think about that, because that's a consistent reduction of costs every day into the future. This is different. This is the present is different from every other day looks the same, but today is special. I just don't want to do it today. Okay, raised by a factor of B. Okay, so that means, think about his reasoning on day T. This all starts to make sense now, right? Because if he sends it today, he incurs a cost of B times C, right? This raised by a factor of B. So C is his cost, B greater than 1 is what he's going to incur. If he sends it tomorrow, well, he incurs the loss of use cost is more salient, but that's a tiny number, plus 1 times C. Right? So C is the big term here. 1 times C is less than B times C. So in fact, tomorrow is preferable to today. And in fact, tomorrow is the optimum. Because after all, the day after tomorrow would be, bx plus x plus c. No point waiting until the day after tomorrow. Okay, so Tomorrow is always the optimal solution. All right, so this was his particular telling of the story of present bias. It was sort of told by a number of authors during this period in the sort of early days of sort of modeling in behavioral economics. It grew into this very rich general framework, which perhaps sort of, most crystallized in David Leibson's 1997 paper on quasi-hyperbolic discounting. And basically, this is just sort of to kind of tie this into that literature, but, for the rest of it, we're just going to think about this factor of B. Right, so basically, in the quasi-hyperbolic framework, a cost or reward C realized T units in the future has a present value that's reduced by beta times delta to the T times C. Delta to the T is our traditional geometric discounting. Right, that just says that, the future always looks like a slightly shrunken version of the present, right? The future is sort of receding into the distance. Delta to the T is a perfectly time-consistent thing to do because it says every day, everything is the same, all just kind of scaled down by delta. Nothing changed, it's all just slightly smaller. The beta is the problem because the beta is multiplied only by things that are in the future. The present doesn't have the beta. So the story I've been telling, is basically delta is 1, because I'm just going to take the geometric discounting out of it because it doesn't really affect our story today. B is just beta, 1 over beta, because this is a number less than 1, this number bigger than 1. And finally, a point that I will actually come back to in some detail, the agent at the moment is naive about their bias. They somehow believe that tomorrow they're not going to have this factor of B, everything will be great. It's just today just doesn't work, Okay, so that's the special case we're thinking about. Now, this is a very simple model, but it actually was capable of producing a lot of interesting behaviors. And so, for example, it was able to model procrastination, as we just saw. It was able to model this phenomenon of task abandonment, right? Task abandonment is the thing where you have this great idea for some project you're going to do, and with a burst of energy, you go and do half of it. And then somehow you never quite get around to ever finishing it, so it just sits there unfinished, which is, whatever your cost benefits were, that is not the optimal strategy. Because either it was worth finishing or it was not worth putting the unused effort into it that you ended up doing half of it. So, but task abandonment is something we also all recognize. And, this nice work of O'Donoghue and Rabin created a sort of nice application of this model, somewhat intricate, to actually create task abandonment to happen under an agent that did this. And, a third thing documented by, Ariel and Vertenbrock originally, and then in a lot of subsequent work, the benefits of choice reduction. That for present biased agents, I can actually help them by eliminating their freedom of action, by taking away options. Right now, for an agent that was optimally planning with knowledge of costs and benefits, it can never help to reduce options, right? If it's suboptimal, you just won't do it. But for a present biased agent, it can actually help to take away freedom of action. And again, relatively complicated constructions here. And so we thought to ourselves, it'd be nice if we could have one framework where we could just sort of, again, derive these stories sort of mechanically, computationally, and sort of not have to sort of have each one be their sort of own intricate application of these principles. Also, if we had a kind of common framework for all of these stories, I could do something that we like doing in theoretical computer science, which is asking about performance ratios. Right, so one tradition that one sees throughout theoretical computer science is to say, I have an agent with some kind of a computational limitation on their behavior, and I want to compare that to optimal behavior. I'd like to compute a cost ratio of the cost by the limited agent divided by the optimal cost, the minimum cost achievable. Right, so we see this, for maybe most famously in approximation algorithms, right? My agent is limited by being forced to compute in polynomial time, and so it can't find the shortest traveling salesman tour, but the optimum can, right? What is the approximation ratio? And we see it with online algorithms. My agent doesn't see the future, how does it do against an agent that can? We see it now recently in things like the price of anarchy, a field that Tim is one of the major pioneers in, where we say these agents can't coordinate the optimal solution, they have to obey a Nash equilibrium, what's the loss? Right? A recurring theme in theoretical computer science. And we thought, there's clearly a price of irrationality here. What is the price of present bias? But we didn't know how to ask the question, right? If we look at the behavioral economics literature, how do I even formulate that question? I sort of want to say, across all stories in which present bias has an effect, what's the worst case ratio, right? So there's the high school graduation story and the gym membership and the trip to the post office. It's sort of like max over all stories S of but I don't know what that means. I don't know how to quantify over stories. I want something I can quantify over that actually captures the range of situations I'm talking about, right? A framework where I can say, here are all the possible instances. I can write down all of these in that framework, and then I can actually ask about worst case bounds, and I can reason about these things. Okay, so how do we do that? So the idea that Segal and I had was all of these multi-step plans can be viewed as graph traversal. right? That's something else that we're fond of doing in theoretical computer science and in a lot of areas of computer science and artificial intelligence and elsewhere, to think about a state space. I am traversing a space of states. I start in state S. I have to get to state T, and there are costs on the edges I traverse. Okay? So this is actually going to be the model that we use for this next phase of the talk. So it's worth kind of dwelling on just to make sure everyone gets how this works, right? So we have to get from S to T. Think of it as you're trying to find the shortest route. I could go this way. That would be 16 plus 2 plus 2 is, that's what, 20. I could go this way is 8 plus 8 plus 8 is 24. Or I could take this bypass, and that's 8 plus 2 plus 16 is 26. So actually, the paths are ordered this way. This is the shortest path. Okay? Everyone sees how that works, right? So if you've taken an algorithms class, this is very familiar. But if not, I just want to make sure you kind of, because we're going to be looking at a lot of these pictures. Right? Graphs with lengths on the edges, so feel free to ask if anything is unclear here. But that's the idea. The optimal agent is going to take the shortest path. I'll come back to why this represents, high school graduation or represents going to the post office. You can sort of imagine there's a sequence of steps that incur costs, but I'll try to be more precise. All right. Now, here was the funny thing, and it sort of was striking to us, sort of how disconnected this behavioral economics present bias literature was from the kind of CS AI planning literature, that this model didn't really exist in the literature. To simply say, a present biased agent has the limitation that when they get to a node, all of the immediately outgoing edge costs suddenly look like they're multiplied up by B. Everything else looks normal, but this very next step looks like it's multiplied up by B. So they make a plan treating these as the costs. But then when they get to the next step, the world suddenly changes. Now, these next edges look like they're multiplied by B, and everything else looks normal. And so that means they might actually change their minds. Let's see how this works, right? So present biased agent is standing here. They look at these three things, and they look, in all my examples, B is 2, just for simplicity. So this one is 16 times 2, 32, plus 2 plus 2. So this one looks like 36. This one straight through looks like 16 plus 8 plus 8 is 32, and this one looks like 16 plus 2 plus 16 is 34. Okay? So now this path straight through looks like the best to them. And it stands to reason. I mean, this is a big cost. You do not want to incur this today. So you're going to avoid it. Okay. So you take that first step, fully intending to go straight through nodes C and D. But you get here and the world suddenly looks different because this 8 looks pretty big. So this is 16 plus 8 is 24. This is only 20. So you change your mind, right? This is actually path planning where you change your mind and now you go this way. And this is actually how you end up going. Right? So two things happen that we should note. One is that you were suboptimal. Right? You did not find the shortest path. And the other is that you didn't even do what you thought you were going to do when you started this. Right? Two things that we recognize from all of the stories, and they sort of happen effortlessly once we make up this particular kind of shortest path problem. Okay. Just to kind of reinforce that I can tell lots of stories this way, here is George Akerlof trying to go to the post office, told as a graph. Because what happens? We're here. Node VI, right? Node V3 is going to represent reaching day 3 without having gone to the post office yet. Right, so N is 5 here. V5 is you got to day 5, the end of your sabbatical, and you didn't make it to the post office yet. Now, when you get here, you have to go to the post office, right? So on any day, you're one step away from being done and out of your misery, which is just, you just pay C and you get to T. You're done. Or you can kind of orbit, right? You can pay X and wait till the next day. And this is exactly that story told as a graph. Now, my point is not so much that, we can tell the story, that we were able to code up that story, but almost the opposite, that it's sort of effortless to tell these stories, right? Every graph you write down is in itself a story that has some meaning. Okay, let me mention one other thing that we can add to this, and then once I've added that, then I'll sort of try to delve into some of the theorems that you can actually try proving about this model. So I can also add rewards, right? So far, there's a task you have to do. Right, you had to send the box back. It's a given that you're not going to abandon it in India. Okay, but there are some tasks where, there's a reward, and I do it if it's worth the reward, as I perceive it. Okay, so here the agent is also trying to find a path to T, but they're trying to optimize reward minus cost of path. But again, the cost is the way as they experience it. So let's imagine what happens here. The agent looks and says, this path looks like 2 times 2 plus 6, the present biased agent, that's 10. This looks like 2 times 3 plus 5, that's 11. Okay, this is better, and it's less than 11, so if I pay this 10, I'll get 11, it's worth it. The 11's in the future, so it's not scaled up, right? Okay, they get here, the world has changed. This 6 looks like a 12, and they give up, right? They stop. It is actually not worth it to them to do this second step to get this reward, because they'd be paying 12 to get a reward of 11. So they actually abandon the task, wasting this work of 2 too that they did. Okay, so actually task abandonment sort of effortlessly happens in this model once you set it up this way. Okay, and again the point is they were naive. So standing here they didn't, right, they somehow believed that the world would look like a cost of 6 when they got here. Again, I'll come back to this assumption of naivety because depending on context, we have, one sees situations where people behave in a largely naive way and also ones where they are aware of their bias. And I'll come back to the question of how do we model that. We also actually get to model the benefits of choice reduction here. If a designer showed up and said, I'm going to help you out. I'm just going to delete node A. It doesn't exist. Then suddenly they have this path, right? This looks like 2 times 3 plus 5. And assuming they break ties in favor of going, then they'll go. They'll actually pay a real cost of 8, right? Remember, however George Akerlof perceived the subjective experience of having to go to the post office, the real cost he incurred was the loss of use cost plus the time in line, not whatever he was multiplying it by in his perception. So here the real cost is 8, you get the 11, and you actually do it, and you get all the way to the end, because I deleted that node to kind of help you out, right? Reducing choice can actually help. All right, let me run through one more example, and I do this mainly to show that, you can actually create some relatively rich structures this way. So thinking about things like completing online courses, for example, sort of quite effortlessly one can write down the story of why people fail, not the only reason why people fail, but sort of a story about trying to complete a course with present bias. So I start in state S, and let's imagine this is a 3-week short course that has 2 projects in it that you have to do. Okay, and the way the cost structure works is, so this state Vij is the state in which I weeks of the course are done and you've completed J projects. So V2, so time moves inexorably this way. Notice how all the arrows go 1 step to the right. So you're just being dragged in this direction no matter what you do. You're trying to get to T. And V21 means it's now 2 weeks have gone by, you've done 1 project. You still have to do another one, right? V12 is a happy place to be. That meant in a burst of energy you did both projects, week 1 has gone by, you've done both projects, now you can just glide to the finish, okay? Now the cost structure. Let's imagine the cost structure, this is just a worked example, so nothing special about this. Maybe it costs 1 to go horizontally, right? To sort of idle for a week, do no project, you pay 1. Right? You're just moving along horizontally. 4 from doing 1 project, okay? And 9 from doing both. Okay, because somehow, if you do 2 projects in 1 week, that sort of eats more and more into your available time. The opportunity cost might just go up sharply. And there's a reward of 16 at the end. I set this up just to kind of get things to work out. Right? And again, it's sort of, my point we have to remember is not so much that, that we can encode, course taking in this way, but that it's sort of effortless to do so. Any graph has a story embedded in it. So what does an agent do here? They say, all right, this route looks like I'll spend 2 times 1 here. And then I'll do both projects in weeks 2 and 3, right? This is starting to be familiar. Anyone who's taught a course has had the experience that, you could tell the class, you're all grown-ups. Here are all 8 problem sets on day 1 of the quarter. Pace yourselves. And anyone who's taught a course and has ever tried to do anything remotely like that knows that is a complete disaster. Because it's just, it doesn't matter how, sort of mature or grown up you are, I would have exactly the same problem. It's very hard to pace yourself. There are other things that happen. And now suddenly there are 2 weeks to go and you've got like 7 problem sets left to go, and you just end up dropping the course, right? And so you end up creating deadlines. Even if you knew the problem sets in advance, you say one's due each week, right? I've eliminated your freedom of action because I'm trying to get you to finish the course. And that's going to happen here in this graph, because this person thinks they're going to do this, but they get here and they say, well, actually, this looks like, what was it? 2 times 4 is 8 plus 4 is 12. But this looks like 2 times 1, and then I'll just do a real burst of energy here. I'm just going to do it all in the final week, and that's only 11. Still worth the 16. No problem. We'll go to last week. But now, 2 times 9 is 18. It's just not worth it to get the reward of 16 from the course. Maybe I'll just drop it. And so you end up stopping at this node because it's no longer worth making it to the target, right? You kept thinking, okay, I'm just going to sort of do everything in one final all-nighter, and then you finally just don't do it. And I could solve everything by just deleting that node. I could simply add one more rule to the course which says you must have completed at least 1 project by the end of week 2. Okay, that's all I ask, which basically just means knocking the corner off of the state space. And now everything works just fine. The person realizes they have to turn the corner here. They do, and everything works out. They get to the target. Okay? So again, this will be the last complicated example I show, just to kind of show you how this model works. But it's sort of for free to build up very, very complicated things, which sort of reproduce mechanically the kind of behavior that we're seeing in these models from the behavioral economics literature and arguably from our own anecdotal experience. Okay. So let me move from examples to some things we can actually prove about this model. And we'll see that some of these are questions we couldn't even sort of ask without having the model at our disposal. All right, so first, this issue of characterizing instances that have very high cost ratios. So we'll see that actually things can get pretty bad. And we'll ask, what is the structure of the instances where things get bad? Then I'll ask about sort of choice reduction, right? There's a very interesting algorithmic problem. I hand you a graph. I would like the present biased agent to complete it. Can you please modify the graph for me, remove some of their freedom of action to get them to finish it? Okay, and that's just an algorithmic problem it takes as input the graph. And finally, I'll come back to this question of agents who are naive versus agents who are sophisticated, who know that they're biased, but are still nonetheless biased. What does that mean? Okay, all right. So first of all, the cost ratio, worst case cost ratio can be really, really bad, right? The Akerlof story is in a sense only the tip of the iceberg, because here's what could happen. This is the Akerlof story again, except going to the post office is getting exponentially more expensive every day that you wait, right? This is almost a story sort of too painful to contemplate. But you know, as time goes on, it's just getting worse and worse. But the problem is the difference between, you know, so now it's at C cubed. Things have gotten really pretty bad. On the other hand, it would be, assume C is less than B. To really do it today would be B times C cubed. That's unpleasant. Versus, you know, tomorrow's C to the fourth, which, you know, B times C cubed, C to the fourth, I'm trading off a factor of B for C. That's worth it, actually. So I'll wait till tomorrow. But tomorrow, of course, it looks like B times C to the fourth. C to the fifth looks better. And you actually go all the way around this loop. And you end up paying this astronomically high cost, this exponentially large cost. OK, so the cost ratio can be actually exponentially bad. Now, so a question that we asked ourselves was, can we characterize the structures that produce exponentially bad cost ratio? And one thing that we really want to understand, informally stated, is must any instance with a large cost ratio contain Akerlof's story as a substructure? Right? Now, again, this is not a question I could even ask about stories, right? What would it mean for a story with an exponential cost ratio to contain another story as a structure inside it? But once I'm in the graph world, I can ask that question. Right? I can ask that question using the language of graph containment. So let me give you some definitions that I'm going to need, and this will be sort of the one theorem that I actually sort of sketch the proof of, and then we'll sort of pop back up to sort of a higher level. Right? So this is what I'd like to formalize. So first let me formalize the question, and then let me show you how we actually proved it. Okay. So what does it mean for one graph to contain another as a substructure? So here we're going to use the language of graph minors. Right? So I'm asking, is the Akerlof graph a substructure of the graph that I'm looking at, which has a really bad cost ratio, right? You hand me a graph with a really bad cost ratio, I'll call it G. H is the Akerlof graph. I want to know is H somehow contained in G. So I'll say H is a minor, graph H is a minor graph G, if I can basically do the following. So imagine H is a graph that has 4 nodes all mutually connected, okay? Then what I could do is find sort of a macroscopic copy of H in G by saying, look at these 4 connected clusters, all of them disjoint, and all of them with edges to each other. If I sort of squint and ignore the fact that there's a bunch of nodes inside each one, it's really just 4 really big red nodes all connected to each other. So, right, this graph K4, right, the complete graph on 4 nodes, everyone's connected to everyone, is a minor of this graph G. Right? Here was the graph G, and it contains the complete graph on 4 nodes by finding these 4 connected subgraphs, all of them disjoint and all of them mutually adjacent. Okay, that's what it means for H to be a minor of G. All right. So what is it that I'd like to look for as a minor, right? You hand me a complicated graph with a very large cost ratio. What do I want to find as a minor? So I'd like to do this, without the arrows and with the weights, so I'll take those out. I'd like to find this. I'd like to ask the question, is this present in any graph that has a very large cost ratio? Okay. So we'll call that graph the fan, right? This is the Knode fan if it has K nodes around the outside. It's the graph consisting of a K node path and one more node that all others link to. Okay? So now we have a definition of the Akerlof story, the fan. We have a definition of containment, and so I can actually now state the theorem, which says for every exponential base lambda greater than 1, there's a positive constant epsilon, so that if the cost ratio in my instance is greater than lambda to the n, right, it's exponentially bad, then the underlying graph of the instance contains a K-fan minor, where K is actually linear in the size of the graph. Right? So actually a constant fraction of your instance is actually the Akerlof story in this graph.
Where is B?
Good question. B is implicit in, so lambda would presumably have a dependence on B. Yeah, right. So imagine the lambda is implicitly parameterized by B. Yeah, thanks. Okay. Good question. Okay, so, yeah.
So is there no dependence on the size of the graph itself?
N's the number of nodes of the graph, yeah.
Wait, but there's 2n. I see. So you're, okay.
Yeah, so this is a k plus 1 node graph. Think of k plus 1 as, right, and then n is the size of the original. The original graph is an n node graph that has a high cost ratio.
But lambda and epsilon don't depend on n.
Exactly, they depend on B, right? So fix B. Now there's, yeah, for every lambda there's an epsilon depending on B and lambda, yep. Exactly. Other questions about this? So here's how actually, so I want to sort of sketch the proof. So this is a proof involving one graph contained and another is a minor. Some of these proofs, you know, these proofs tend to have a sort of similar structure. Some of them are very long. This one is actually relatively short. But they tend to consist of, let's use what I know about the graph and sort of piece together this minor bit by bit, right? Because constructing a minor is this question of finding these connected clusters that are all disjoint, that are going to model the K-fan, and then sort of wiring them together so that they're all connected. And all I can use is the fact that there's a high cost ratio. All right, so here's how this proof is going to work. And again, I'll sort of spend about 3 slides on the proof. This will be the most technical part, then we'll pop back up. All right, so why did I have a huge cost ratio? Well, because the agent started at S, and we don't know quite what it was doing, because we don't really know what the graph G looks like. But it was walking along, trying to get to T, and just sort of going from one node to another. It's traversing some path P. Now, let's say the d of VW is going to be the weighted graph theoretic distance, right? So from any point, there is a genuine shortest path distance down to the target. And I'll say the rank of a node is basically the logarithm of its distance down to T. Okay, so actually formally, it's sort of the logarithm compared to the distance from the original point. So a node has rank V if its distance to the target looks like b to the j times the distance from the original thing. Right, because as you set out, if you're going to have a huge cost ratio, in some sense, your distance to the target is actually getting bigger and bigger and bigger. That's why you got the big cost ratio. And so it's sort of lifting off in that sense, and the rank is going to track that. Right? The rank is the log of your log base b of your distance to the target. Okay. So here are some claims that we can make about this structure, right? So I'm basically watching the path the agent takes. I'm going to try to build the minor off of the path the agent takes. And I'm going to track the agent's progress using rank, right? The rank of the current node they're at, the logarithm of their current distance down to the target. One thing you can notice is the rank has to be getting bigger, but across any one edge of P, one can prove that actually the rank increases by at most 1. I won't get into the proof of that, but basically, at any point you always have the option of taking the shortest path down to the target. But you didn't. And if you went this way, it was only a factor of b that was differentiating them. And if it's only a factor of b, the logarithm base b is only going up by almost 1. It was roughly the idea. Okay. Secondly, a sort of clear point is that if you're going to have an exponential cost ratio, at some point you're actually incurring an exponential cost relative to the optimum. So there's going to be a node that actually has rank at least epsilon n. Okay? And that means actually you're eventually traversing an edge that has a very, very large cost. All right, now let's build the minor. So let's look at this sort of ramping up. So the prefix of the path until the rank first reaches epsilon n. Right? Things are getting worse and worse and worse. They could be temporarily, transiently getting better, but on net they're getting worse. So they go up and down, but let's say Vj is the last node on this path of rank j, right? So this is the last time you're ever at rank 1 until you end this prefix. This is the last time you're at rank 2, last time you're at rank 3. Okay. From these nodes, I can think about the shortest path to T, right? So from V0, the last time you're rank 0, there was a shortest path down to T. And an interesting fact is that this prefix, P star, and Q0 don't share any nodes. Why is that? Because this is the last time you're at rank 0. So this thing only goes up, whereas this one only goes down. It's the shortest path, so the ranks just get better and better and better. Right? So these two things actually diverge and never meet again. So they're disjoint, because remember, I need disjoint pieces for my minor. Similarly, the path that drops down from V1 is disjoint from the rest of this, because they never meet again, and so forth. And now I actually have my fan minor. Right? The fan minor is going to be these k nodes, and I'm going to contract all of this into one giant supernode that is adjacent to all of them. Right? So from watching the progress of this thing as it lifts off through the ranks, then contracting this gigantic glob of things into T, I actually have produced a fan. Right? So the fan must be present anytime you incur a high cost ratio. Okay, so that's the FK minor. And actually, this argument has a lot of slack in it. I mean, we're sort of throwing away things left and right. There's actually some nice follow-up work, and I'll mention a couple of follow-up papers as we go along. This work of Tong et al., which actually finds sort of the exact tight bound, which says, in particular, the fk minor occurs exactly when the cost ratio is b to the k minus 2. And what's nice about their theorem and compared to ours is ours actually had a dependence on n, the size of the graph, and theirs doesn't. Theirs says if the cost ratio is large enough just relative to b and k, then you actually have this minor. It didn't matter how big the graph was. Okay, so that's the minor. All right, let me talk about a couple of other algorithmic problems, and then yeah, question.
So we could also perhaps care about the weights of pandas.
Yeah.
Is there a way to refine this argument to say that not only is there the minor, but sort of
There's sort of a way to, yeah. So in fact, there's a lot more structure going on here. In particular, there's kind of a fan minor where the costs are exponentially going up. Sort of the language of minors doesn't tend to have a way to cleanly talk about weights, but one could sort of, with a more elaborate definition, definitely do something like that. Absolutely. Yeah. Let me talk about choice reduction, and then I'll just wrap up with some thoughts on sophistication. So, choice reduction. So remember the sort of miracle of choice reduction was if you're a designer, you could actually come in and say, I'm going to eliminate this node, and I'm going to actually thereby allow you to traverse the graph. So that's an algorithmic problem. Given a graph G not traversable by the present biased agent, is there a subgraph of G that you can find that is traversable, right? That's your goal in sort of creating problem set deadlines or eliminating other distractors to get the person to finish. All right. We actually thought this question, when we first asked the question, we thought this question would be easy, and then we would kind of move on and try to find harder questions. Because here's how we reasoned. If there's a way to delete stuff and get the agent to follow a path, what I should do is just rip away everything but that path, present them the path, and they'll just do it, right? Isn't that what's going to happen? So it's just a question of like finding that path that they're going to do. And that turns out to be false. It turns out that there are graphs that an agent will follow, but there is no path in that graph that if you present just that to them, they will follow. A little counterintuitive. Here's how this works. Okay, so this is an example that we sort of didn't even really think could be there until, but it isn't a very hard example. So consider this example. There's a reward of 12 at the end. We have to sort of think through this. The agent at the beginning says, okay, I'm going to decide, is this worth going to the reward of 12? Well, let's see. So 2 times 2 is 4, plus 6 plus 2 is 12. And in case of tie, I'll go for it. So yeah, I'm going to go this way. The agent goes this way. They get to A. Now they go, oh, actually, 2 times 6 plus, that's 14. But fortunately, this path comes to the rescue, because 2 times 3 is 6 plus 6 is 12. They keep going, and they make it. Now imagine I deleted any one node from this. Well, if I deleted this node, node C, then when they got here, they'd give up. They'd start out, but they wouldn't make it. And if I deleted node B, they'd never start in the first place, because this looks like 4 plus 3 plus 6 is 13. So this is actually a minimal traversable graph, right, which has no individual path that they would traverse if they were presented with that. They actually need the kind of misdirection in order to ever do it. And we thought about this. It's sort of rare that you ask, is my counterexample ethical, right? Like, am I misleading the agent somehow? That's sort of what's going on. But there's sort of multiple ways to think about this, right? This is sort of, you sort of think, right, what story is this graph telling? There's sort of many stories. Some of them are kind of unsavory, right, that you're sort of diluting the agent. I mean, there's also sort of the version where, there's sort of the 6-year-old child, and you're trying to sort of convince them that violin lessons would be a good idea. And you say, okay, so they end up watching lots of YouTube videos and see these violin virtuosos and say, yes, this is a good idea because I could be a violin virtuoso. And so they, they take some violin lessons, and then they get to this point where they discover you're going to have to practice many, many, many hours a day to really be a virtuoso. But at that moment, they realize that actually doing the violin is a really pretty rewarding thing, and they take this other path, and they end up having this rewarding experience playing the violin, but not for the reason they thought. Right? So no YouTube videos, they would never have started. But no non-virtuosic way to continue, and they wouldn't have made it to the actual proficiency of the violin. Right? You actually needed both for them to actually get there. And that's effectively what this example is saying. Okay, so then we're like, okay, this is a real problem on our hands, because we have a graph, we want to find a subgraph, and it could have a complicated structure. So, right, so in fact, a few groups afterwards, sort of, after we wrote this paper and put this out as an open problem, this paper of Tong et al. I mentioned before, as well as Uri Feigen's separate work, proved that it's actually an NP-complete problem. Given G, given the parameter B, is there a subgraph that's traversable by present biased agents actually NP-complete to actually find whether so we don't actually expect there's going to be an efficient algorithm for this. Okay, let me talk about one more thing. and then I will wrap up. So we've been talking about, how these agents behave, and there are lots of situations where people are, and especially in these cases where you see extreme procrastination, it's sort of a sign of this kind of naivete about this optimism about what's going to be true in the future, right? You don't have a realistic assessment of what you're going to do in the future. There are other situations where it's, people are sophisticated, right? Where you're aware that you have this tendency to be present biased, and you would like to correct for that. Of course, you also don't want to do it today, right? You have two things going on. It's not that makes you want to do it today. It makes you wary of what's going to happen in the future. Let me, so there's actually, we want to sort of bring this into the graph theoretic world. And for that, we went back to the same work of O'Donoghue and Rabin, who actually had a nice articulation of sophistication. And it's based on this sort of competition among your present and your future selves. Right? This present versus future self is a metaphor you see a lot in the behavioral economics literature. I could have used it with the naive agents, but we arguably didn't really need to. But here, pedagogically, it's actually useful, right? Essentially, the present self, wants to eat the giant cookie, but the future self is going to feel really kind of gross 2 hours later from having eaten the cookie. And so there's this kind of battle going on, right? The present self really wants the cookie, but the future self would really rather you didn't eat it, right? And that's the tension. So, as an example, how does this tension play out? Say it's Thursday. You have a NSF progress report that's due at, these Saturday midnight deadlines are the worst. You gotta hate these things. So, okay, so there's a cost depending what day you do it. You have to do it. So if you do it Thursday, it's okay ruining your Thursday night. That's a cost of 3. You'd rather not ruin your Friday night writing it, and you'd really rather not ruin your Saturday night doing it. That's the cost. Okay, how do you reason if you're a present bias agent, but you're sophisticated? Well, on Saturday, you have no choice. You have to do it. The cost is 9. You're going to perceive it as a cost of 18, but you're going to have to do it anyway. Okay, your Friday self perceives the current cost as 2 times 5 is 10, whereas they perceive, they're aware that their future self won't want to do it either, but the cost to them in the present, right? So the sophisticated agent cares about the cost in the future multiplied by 1. It cares about the present cost multiplied by 2. So it says, all right, I'm going to make the Saturday self do it. Because to me, right, the Friday self is gone at the end of Friday and hands off control of you to the Saturday self. So the Friday self does feel the pain of 9, right? They don't want to experience the pain of 9, but it's not as bad as experiencing 2 times 5. So the Friday self pushes off. Now the Thursday self actually does something clever. Because the Thursday self perceives the cost as 2 times 3 is 6. But unlike the naive agent, who would have just not done it, the Thursday self knows how the Friday self is going to reason. And they know that the Friday self is going to hand off to the Saturday self. And that's going to be 9. And this is only 6. Yeah, it's 2 times 3, but that's still less than 9. So the Thursday self actually does it. Right? And that's not what the naive agent would do. The naive agent would believe, because what does the naive agent say? They say, oh, this is 2 times 3 is 6, but on Friday I'm going to really feel like doing it, so it's only going to be 5. Right? But the sophisticated agent is too smart for that. Right? They say 2 times 3 is 6, that's less than 9. Okay, so they actually are going to do it right away. Right? So it's this kind of selfish arbitration among your present and future selves where you sort of favor your present self. Right? Your present self gets this factor of 2 in its favor, but you still add up all the costs. You still care about the cost of your future self, just not as much as your own present. Good. Right, so this is sort of variously described by behavioral economists, these kind of examples, as basically you're sort of playing a game of chicken with your future self, right? Who's going to have to do it? Right? Okay, so can we put this into the graph theoretic framework? So here, Segal and I played around with various ways of doing it. We embarked on this very interesting work with Manish Raghavan, which has been a lot of fun to pursue. And there is sort of a, one can put this into the graph theoretic framework and start asking questions about it. So here's that story. You could do it today for 3, note the fan structure, because you're procrastinating. And if you're procrastinating, then there's a fan in some sense, right? So you could do it now, you could wait effortlessly and do it on Friday for 5, you could wait and you could do it there. Right? So there's now a self for each node. There's a V2 self, a V1 self, and an S self. The V1 self says this would cost 9, this would cost 10, I'm going to go this way. And the S self therefore overrides and says, I know that if I get to here, it's going to cost me 9. And so I'm going to go this way and pay only 6. Right? And so now there's an actual algorithm, right? The naive agent, you can sort of just think of shortest path as a black box. It's just shortest path with everything scaled by 2. Here you're actually doing basically dynamic programming, working backwards over this ordering of the graph from T working back to S. as long as by induction at every step you know what your future selves are going to do, you can therefore figure out what your present self should do. And you just keep working backwards until you get to S. Okay, so this sort of is hinting to us that you can't build up long fans because the current self sees that long fan distance and actually vetoes it. It overrides it and it actually gets to the target. This is not to say that the sophisticated agent is always optimal. Certainly not. Right? There's a very simple example. So here, you could do it today for a cost of B. You could do it tomorrow for a cost of C. Now, if C is less than B, then this looks like B to you. This looks like C. And you certainly make your next step self do it. Right? So you can be as bad as a factor of B here. Right? If that's 1 in B, then you're a factor of B worse than optimal. Your real cost is B. It could have been 1. Effectively, that's what your Friday self was doing when it made your Saturday self do it. So, but we had a hard time building up large fans because the instant you try to start getting the agent to procrastinate, the sophistication kicks in. They're like, I'm willing to procrastinate a little bit, but I'm not willing to let this get out of hand, right? Okay, that's not a proof of anything, but we play with this, and Manish actually found this very, very nice theorem that shows this really remarkable difference between the sophisticated and naive case. In every instance G, a sophisticated agent incurs at most B times the optimal cost, right? This little 3-node example for sophisticated agents is the worst case. It cannot get worse than this. Okay, so, right, the worst case is actually exponentially better than the case of naive agents. Now, there is sort of a common generalization going on here, and I'll mention that. That'll be my last slide, and then I'll just wrap up. So what's the common generalization, right? They're sophisticated. You have perfect understanding of how your future self will behave. There's naivete, where you think your future self will somehow miraculously be optimal. You could have some kind of partial understanding, right? And so here, this is sort of the final piece of the O'Donoghue-Rabin framework from behavioral economics. You could say partial naivete, partial sophistication, right? You could imagine the agent believes that its future selves have a present bias parameter of B prime, which might or might not be B, who knows, right? So if B prime equals 1, that's a naive agent, right? They believe that in the future, you're going to have a present bias parameter of B prime is 1, you're optimal. If B prime equals B, that's sophisticated. You actually correctly understand what your bias will be. But it could be anything, right? That could, right? Naivete, and the fact that we see naivete in the world means it's possible to have a misunderstanding about your present bias. And there's no reason that misunderstanding should be that you'll behave optimally. It could really be anything. So one can generalize everything I've talked about. And so this short statement of the theorem here sort of shovels in everything we've done so far and then a bunch of other stuff one has to do. That there's actually a sharp transition right at sophistication. So if B prime is less than B, as in if you're optimistic about your future selves by even a little bit, then I can basically get the fan going, right? All you have to do is be even slightly optimistic, and then you say, sure, I'll leave this till tomorrow and so forth, and you actually end up with the exponential cost, right? It does not degrade gracefully, right? If you miss by a little bit on the optimistic side, you can be in big trouble. Whereas if you're pessimistic, you can't get the fan going, and we can generalize the previous theorem to say actually the worst case is B prime. For any B prime gradient will be. Right, so pessimism in this case is about your future self is much safer, right, exponentially safer than optimism. Yeah?
Does this require you to have sort of linear foresight in
Yeah, good question. Yeah, so this is really, right, so there are a lot of interesting questions you can imagine that here I'm imagining I know the graph structure and I have I consistently believe B prime. You can imagine, for example, the case of the unknown graph is an interesting question where one would have to think exactly how are we modeling that. The case of different varying sophistication, that is easier to model. You can imagine that K steps in the future, I have an estimate BK on my sophistication, on my present bias. And now you could ask sort of for that sequence, what's my, yeah, and that would be a very interesting question, which one could essentially write down exactly in this framework. Yeah, nice question. Yeah?
So this isn't, if you know that you know that you know,
yeah, so
then things actually do change, right?
Yeah, so if you yeah, this is only one level. But I mean, naivete is only one level, right? It basically says, I believe I'll be optimal, yeah. Right, so you could ask about sort of these higher order beliefs, yeah. This is why, and this is where it, although it...
The Rumsfeld...
yeah, the unknown unknowns versus the known, yeah, exactly. This is why it sort of took us a while to really decide what we wanted the graph model to be, because when you just think about intuitively, you say, okay, let's think about sophistication. You have to convince yourself, why are they not, if they know that they're biased, what's the problem? Right, but the point is, they're biased and selfish. They don't want to do it today. They are willing to push costs onto the present. So, it's the same sense that you have this problem, but you indulge in it anyway, because you really don't want to do it on Thursday, right? So that's some of it. So the difference between the knowledge and you still have a cost structure that favors not doing it today, and that's somehow the.
So I was thinking about the sunk cost fallacy.
Yeah.
And that's quite the opposite of what you're working on.
Yeah, fantastic question. So this is actually what Manish and Segal and I are thinking about at the moment, which is, so the sunk cost fallacy is in a sense almost the opposite of present bias. Let me say it with the health club. In the health club context, it says, I don't feel like getting up this morning, but I already spent the $30 on the health club. I don't want that to go to waste, right? That's a fallacy in the sense that the $30 is gone. It doesn't matter if you get up at 6 a.m. You spent the $30. You should decide what's optimal like right now, right? It's the same sense that you bought the concert tickets for $10, and now it's like, driving rain, dangerous conditions for driving. I have to use rain here in Palo Alto. I would say snow if I were in Ithaca. But it's driving rain, and it's just not safe to go to the concert. You say, well, but I have to. I spent the $10, right? That's a fallacy. The $10 is gone. You should decide, is it worth going to the concert at the expense of driving out in these dangerous conditions? The answer might be no. Yeah, so that's the sunk cost fallacy. And so one thing we're thinking about right now actually is that the sunk cost fallacy is sort of working also as a partial antidote to present bias, because you spent the $30, you don't want to get up at 6 a.m. the way you thought you did. On the other hand, you also don't want to waste your $30, right? And these two biases are in tension. Yeah, very, very interesting question, yeah. And we have some results happy to talk about afterwards. Okay. Let me wrap up. Happy to take a few more questions after that. So, reason about long-range planning, right? And it really requires this model for decision making, right? We started with this model in the behavioral economics literature, which was really quite rich at producing behaviors, but it produced them sort of in many different ways. We wanted a common framework, and this graph theoretic framework, I think, lets us ask it in a unified way. It uncovers new questions. It really lets us ask questions that, as I said, we didn't have the language to ask without it. Okay, a number of open questions. I just sort of documented a couple of them here that the first one I already talked about, right? Traversable subgraphs for naive agents. It's an NP-hard problem. Could I do something clever where, for example, I approximate it? I increase the reward slightly, so I do some kind of double criterion thing where I increase the reward slightly and I delete nodes and try to come near the optimal solution. Right, I've now allowed myself slack in this other dimension where I increase the reward. And maybe that makes it something where I can actually prove some approximation guarantee. You can add rewards to the sophisticated model. Wasn't able to go into that here. You get some nice questions there too. In particular, it turns out to even be an open question to us to find the minimum reward needed to motivate a sophisticated agent to reach the target. Because the way rewards behave in the sophisticated model is very, very complicated. It's possible to have a reward, the agent will do it. You raise the reward, now they won't do it. You raise it again, now they will do it. It's a weird thing, which I'm happy to show you afterwards, but it took us a while to find this example also. But it says, I can't even binary search on the reward because it goes on and off as I go. And of course, there are richer reward structures. I could put intermediate rewards in the graph. I could do lots of things. There are a lot of other questions that you can imagine, right? Multiplayer settings, right? Imagine that there are agents competing with each other. They have different levels of sophistication, maybe different levels of knowledge about their opponent's sophistication. Very interesting questions. And of course, all of these potentially feed back into the way we reason about how we design these environments. Badge design, and many other incentive structures as we look at these online platforms where people set these long-range goals. And so I think, there's some very interesting developments here. As we, as a, community of people, who think about computing platforms, are really designing the systems in which people set goals for themselves and set out to reach them. And I think a lot of the sort of theoretical ideas, around path planning and graph traversal are really going to be very, very important for thinking about this going forward. Thanks very much.
Time for a few questions?
Yeah.
In a democracy, there's sometimes disagreement as to what the graph is. For example, global warming, the Republicans believe one thing, but the opposite. How do you combine that with democratic?
Yeah, so as you're pointing out, we could say there's actually a sort of societal present bias. Like, we need to kind of slow down various things in order to sort of protect the planet, but it's going to hurt us in the short run to slow down things. Yeah, and so I think that, when we think about sort of societally, how do we traverse this graph where, there's an endpoint, which is, catastrophic global warming, and there's an intermediate stage, which is sort of slowing down the economy. several things go on there. One is disagreement. Each of us thinks there's a different graph who has the decision-making capacity. And the other is we have different reward structures, right? So my reward structure is that I would like to get reelected 2 years from now, and so I would like things that are sort of good for the next 2 years. Other people's reward structure is I would like, my grandchildren to live above sea level, and so that I have a different reward structure. So yeah, and so now we have a different cost structure, and so I think, yeah, that gets into sort of multi-agent decision making, right? How do we sort of hand over control when we disagree on the cost structure? Or maybe we have genuinely different cost structures, right? Yeah, I think all of those are very, very good questions. Yeah.
Curious, so it sounds like in Akrilov's original sort of model or scenario, he actually didn't end up going to the post office. So he never actually paid this.
For accidental reasons, but yeah. Yep.
Yeah, so I'm curious if there's a way to model this in certain
Yeah.
people looked at that.
Yep, that would be geometric discounting. So remember I said for simplicity, we're just going to have the B parameter. There is also a delta parameter, right? The delta parameter is that after every step, the cost shrinks by delta. That's off, and there are many motivations for that, but maybe the most intuitive one is to say, with probability epsilon, this problem's just going to all go away tomorrow. Something magic's going to happen. They're going to cancel the assignment. I shouldn't start the assignment now. They might cancel it, So I don't do it. Now, what does that mean? That means all of my costs in the next step look like 1 minus epsilon times what they are now, because there's an epsilon probability they all go away. And so you basically add that to the model, and then you would have that, yeah. Yeah.
We could also divide an edge into 2 parts.
Yeah.
And make it
Yeah, this is a great question. So another thing in our design space, which is a very good point, I could take an edge and I could subdivide it. I could say, no, it's not a single step of cost 6. It's one of cost 3 and it's another cost 3, right? This is the part where in your course you say it's not one project. It's first submit your project proposal, then submit milestone 1, and then, right? And you've turned into something that feels manageable to people. And present bias is actually a great model for how that can actually make something manageable, because now you're only feeling the present bias in the immediate step. Yeah. So I think that's also in the design space. Now, if you subdivide really, really finely, of course, I can almost eliminate present bias. So presumably there's a constraint that I can't arbitrarily finely divide it. But if I could do limited subdivision, what would I do? Yeah, very nice question. Yeah. Yeah.
For the NP-hard design problem, is there a class of graphs that where you do have some positive results, or can you talk about the reduction and what types of graphs they create?
Yeah, that's a nice question. So it's a 3-sat type reduction. So there are these sort of long stringy graphs where sort of things thread through variables and then clauses. And so they certainly, for example, have high tree width. They're highly non-planar. We haven't actually thought that much about tractable special cases. Like, it has the feel of something, which unbounded tree width graphs might be tractable. But yeah, there could even be surprising special cases. But yeah, the reduction certainly produces graphs of this sort of potentially very large tree width.
Maybe this has to do with richer reward structures, but you talked a lot about choice reduction, and I was wondering if you thought about choice addition, like in the story would be providing extra incentives to people.
Yeah. That's a very good question also. How would I either add choices or in some sense adding intermediate rewards is not quite adding choices, but it is, yeah, so you'd want to do that in a controlled way, right? So we thought about that. And of course, whenever you try to theoretically model this, you have to say, okay, the rules have to disallow a 0 cost edge from S to T. It'd be great if I could add that. Then you would just take that. Everyone would take that. So I can't somehow do that, but I should be able to add things in a controlled way. Maybe I have a vocabulary of allowed additions to the graph. Like, you're allowed to do any of the following additions, choose K of them or something. Yeah. I think there are a number of interesting questions in that form. Absolutely. Yeah.
One of the things, as best I understand about behavioral economics, is that you have sort of this menagerie of different effects which can come to bear on how someone behaves, and then they're often stated in these very simple, almost axiomatic forms. And something I'm curious about is there benefit of some of these ideas to conducting more elaborate experiments in behavioral economics, which might be able to distinguish between those effects?
Yeah, it's an interesting question. So I think as a sort of motivator for the design, so as you're pointing out, right, there are a lot of different effects, and this discussion, for example, about sunk cost bias and the tension it has with present bias is one of many examples. I think, one thing this could suggest is, insofar as this suggests particular strategies for design, you could ask now, if I go into the lab, are these actually good strategies for design? So for example, suppose I have an activity you're supposed to do, and I don't quite know your level of present bias, and I don't, obviously it doesn't have such a simple functional form, but there is something concrete I can do. Whatever your actual response to the present versus the future is, and it won't be this simple, if the model suggests you will be more effective if I eliminate the following two options, I could ask, here's the version where I eliminate these two options, do I actually get improved performance? And so as a guide to, different levels of performance through different levels of choice reduction, I could ask, are there strategies that sort of conform to what we actually would see in experiments? So I think that would be one way, and there are many others, certainly, yeah. Yeah, that's a good question. Yeah?
So this idea of intermediate rewards brings to my mind an idea of having impossible final rewards, such that you guide the agent through hard times and then through a
Yeah, right, so I think you can imagine, and this actually gets back to the question of is my construction ethical, for example, that you can imagine rules for intermediate rewards that say, it should be, a sort of non-misleading reward, for example. Like, it should be something where the agent actually comes out with a net positive payoff after, right? So imagine, as a site designer, you're allowed to put down intermediate rewards or, edges or so forth in such a way that you induce the agent to do it and they actually reward minus real cost incurred is non-negative. And that could be an important constraint because it's very easy to sort of keep misleading the agent to thinking they're getting there and then they've incurred a lot of cost and didn't actually get there. So I think that would be a very natural constraint to put in and one that would be reasonable in almost any context. Yeah, I think it also means it's an interesting way to sort of diagnose cases where one doesn't see that, and to ask, that's sort of something which is wrong with this instance, could we fix it, for example? Yeah. Yeah.
Can you talk about that example that you mentioned about in the sophisticated case when you increase the reward, some people start rejecting and then
yeah. So the exact details I can show you offline so we don't run it. But the quick version is essentially there are cases where if I have a high reward, so I could do it today or tomorrow. Tomorrow's more expensive. I want to do it tomorrow. For a high reward, the sophisticated agent will actually procrastinate and make, the Friday self will make the Saturday self do it because the reward's high enough that the Saturday self will do it. If I bring down the reward, the Friday agent reasons as follows. I want the reward. It's worth it to me. And if I procrastinate, the Saturday agent actually isn't going to do it. They're going to say, this is too much, I give up. So by bringing down the reward, I actually force the sophisticated agent to not procrastinate. And so they do it immediately. And so that's step one. Step one says that that doesn't happen with naive agents. Naive agents always believe they're going to follow the same path. It's changing, but at a given moment they believe something. Here, as I bring down the reward, the plan I make now can actually change because I no longer trust my Saturday self to do it when the reward gets too low, but I still think it's worth it. So that's sort of step one. Step two is you need to sort of extend that to say, as I bring down the reward, there's this intermediate zone where it's not worth it and I don't trust my Saturday self to do it and I just don't do it. And then somehow as I bring it down more, now I go do it. So that's the rough idea, but I'm happy to show you more details. So, yeah. What do you think? Should we?
Okay, let's thank John again.
All right, thanks very much.